we're going to talk about sort of statistical modeling of within and cross scenarios, the ones that are available, and also within and not within, sort of within actually, and cross ensemble members. The rest of the stuff that should be in the title didn't render, so I'm Ivis from University of Exeter, an Outreach project, and so on and so forth. So yeah, I'm going to focus a bit on, because previous times I sort of talk about how we build the statistical model, a sort of a spatiotemporal model for how we will model the spatiotemporal distribution of the climate variables. But I didn't talk about, at all about how we actually sample from this thing, because I mean you can construct anything you want, but how do you actually sample from it? And it's very important, especially for very large data sets. Now the main point of this talk actually here is like conditioning on different data sets, and conditioning in particular on different RCP scenarios. Because again, like we have the UKCP, we have only one scenario, the 8.5 for 12 kilometers, which we are supposed to downscale from down to partial level. And then the 2.6 scenario is only available at 6 kilometers. There are other data sets sort of simulated differently. But again, like the whole point is to be able to condition on different data sets, different scenarios, so that we can get 12-kilometer data for all scenarios. And then within ensemble members, and just to keep it to sort of remind everyone, different ensemble members in the climate scenarios means they're initialized with different initial, they start the simulation with different initial conditions, and then those sort of result in sort of a different picture of the climate. For past data until present, you can sort of calibrate with that because you have real world data. For the future is where they start to diverge. I'm not going to go into like how much they actually diverge, how the dynamics diverge because of initial conditions. That's still an open question, sort of. But here the point is that we need to find some way to, again, condition on future climate data, because the past one is sort of the easy case. It's for the present to future. And that's being done within the sort of, again, the ensemble members. But that's sort of one level below the RCP, some different scenarios. Although I'm not going to get much into that because like it's not really an issue to discuss at this point in time, although I have to deal with it. It's the fact that the divergence between ensemble members in a lot of cases is actually higher than within RCPs, but across RCPs, but again, that's a sort of different issue altogether. And I'm not going to resolve it. I mean, it was created like that, so let's just leave it there. So again, the idea here is that we have some posterior. We have a likelihood, there's far data, we construct it however we want, whatever distributional assumptions we make, however complicated it might be, but at some point we need to sample from it. We multiply with some priors for all the different parameters and hyperparameters. We build a very fancy, wonderful hierarchical model, but again, we need to sample from it. So we can start with vanilla MCMC, which for high parameter spaces, it's sort of not particularly great. And especially it's not so much the problem of high dimensionality, it's a problem of the shape of the parameter space. For example, here, it's a two-mode target. It's not very particularly hard, especially if the modes are not far apart, but you can see where a simple random walk will struggle, because it's the sort of low probability areas here that will struggle to get passed by. Again, they're nearby enough, so that's sort of fine. This is the normalized PDF here. We can sort of take it's not exactly the inverse, it's like the exponential of the negative of this, normalized, but let's call it energy. And you can see how it's sort of easily for the particles of the random walk to fall within the lowest energy states present here. Now, I switched to the energy sort of nomenclature here because what we're actually going to use here is Hamiltonian Monte Carlo, because we're going to use tan to do the inference. Why? Because there's no point in inventing the wheel for this simple sort of posterior we'll have initially. It's implemented in C++. It's as fast as it can be. The people that are behind it know what they're doing, so we're going to stick to that for now. When the likelihood and the posterior becomes more complicated, anisotropic, non-stationary, maybe becomes intractable, maybe they're doubly intractable, we'll do the entire thing ourselves. But that's for the future. And that's, again, assuming that this is not enough, which probably is enough. So again, the more complicated target here, the energy well, again, this is where sort of random walk MCMC might get into trouble. I mean, not really, because it's sort of a simple target, even shape-wise, but it's going to be slow. Hamiltonian Monte Carlo takes advantage of the dynamics of this. Why? Because it's based on Hamiltonian dynamics. So it includes the parameter R here, which is the momentum. I'm not going to go into the Hamiltonian formalism in physics, but it goes through sort of a trajectory when the sampler sort of runs. It's not just random steps with some proposal mechanism. The proposal here is some sort of dynamics. It needs to calculate, the per step calculation is much larger than standard MCMC, even if it's adaptive, because it needs to sort of solve a given ODE, it needs to discretize, blah, blah. But again, it's better for more complicated targets. It samples much faster for very sort of peculiar targets. Doesn't do so well when the target is multimodal, but that's not going to be really the case in the simple sort of initial spatiotemporal model. And what's our spatiotemporal model here? Here we're just going to assume that the data are conditionally. They come from some sort of Gaussian distribution, which is, again, sort of fine for the wind speeds. It's not obviously the case for rainfall, temperatures sort of, but the others are not really Gaussian. But again, let's stick with a Gaussian here, F. And we're going to assume here that, I mean, these are usually in a sort of trivial linear regression or multilinear regression models, the covariates. I'm going to sort of talk about later what the covariates can be, but for here, assume this and these are 0. So we only have like a spatial structure effect, which can be decomposed into the spatial one, F, and the temporal one, delta, and the gamma is completely structured, just some more noise. Now the formula here, like sort of, I mean, don't pay too much attention to this formula. Just assume that the phi's are actually come from a multinomial distribution, where the Q matrix here is based on the adjacency matrix, so where the points are, which is trivial for a gridded data as we have, and some other parameters which need to be inferred. And the same goes for the temporal one. The temporal one is sort of easier because it only depends on the previous and the next data point. I mean, you can increase that dependency arbitrarily, the same thing as a special one. But again, here, we're just going to have this data phi, the sigma that goes into the final model, the precision, the variance, the inverse, whatever you prefer, and some other parameters, tau. The tau goes into the, not this tau, this is a different one, goes into the Q for the phi calculation. So again, many parameters of the distribution of our data, what your likelihood want to be, what actual kind of model, do you want the spatial dependency to vary, do you want to be constant, how much do you want to vary, how should the neighborhood points be sort of influence the main point, the central point, and so on and so forth. Again, everything gets sort of incorporated in the likelihood times the priors. You have a posterior, you can sample from. And it's again, it's going to be a Gaussian here, so it's not trivial because it's sort of a fairly large likelihood because the data are a lot of a large number. But again, this is the phi I talked previously. This is the main thing we want to infer actually here because it's the structure effect. It's what's going to give us the sort of the skeleton of our structure of our spatiotemporal model. In this case, it's going to be just spatial one at the beginning. So we're going to infer this F and the sigma for our data. So here are sort of, very sort of trivial outputs you get from any MCMC sampler. For the alpha goes into the calculation of the Q matrix here. Tau, it's dt. D is the some matrix times t. and the phi's. You can sort of get this is an output of 4 chains running parallel. Why 4 chains? Because no reason. It was just sort of reasonably fast because it ran like 10 minutes. And they don't seem to they sort of seem to mix reasonably well. They don't get stuck in any particular mode. The posteriors seem to agree, sort of, except this one, for example. And again, sort of a good run. But what we have now, we have distributions over the parameters, which means we have however many samples we have, that many models from which we can actually sample our data from. Now again, this is just building one model for one ensemble member for one time slice. You extend it, you add a temporal component, another set of parameters, another combination of parameters to give you even more possible likelihoods for which you can sample from. And that's just the ensembles, however many ensembles you have. Now you can condition on other data sets. How? Well, now I said only these were 2, 0 before. Now you can treat the other data sets as covariates, or you can just treat the entire data set as conditional, the actual model here, as conditional on the other data set being another RCP, being just the mean, instead of just a covariate, because then you also have to calculate the coefficients. Now, which approach is going to give sort of better results remains to be seen. But we're just going to start here as just taking some fixed mean initially, then some other ensemble members, then some other RCPs. Keep in mind here, sort of an obvious question would be, when at a different resolution, you have 5 times more data per dimension, 25 times more data. How do you incorporate that into the model is conditioning? You aggregate.
Can I ask a clarifying question?
Yes.
Just because I didn't understand something. So do you mean that then the 60-kilometer data would be the O in that equation? Or would it, because it's gone through that nonlinear G mapping?
No, I mean,
Would it be an X?
the G is sort of just right directly here. In that it would be just an identity, it would be like just a mu.
Okay.
You don't need to transform it. You transform it because this was insufficient, so you want to make it even more expressive. But it can be just a mean with just a structural component here, or it can be the actual covariate.
But you said it would go in the O or the X?
Yeah, no, that's the thing. Either you decide which one's going to be. So, yeah. Yeah, what I just said. Now, this is fine, but it's not particularly useful, as you can imagine, to just have some data, one RCP or one ensemble member, conditioning on some other ensemble member, and then so what? The point is to incorporate all of them into one sort of total spatiotemporal model. So you can imagine how this, again, don't treat G as like some transformation function, just treat it as the identity here. It's not going to transform anything. But you can imagine how all different ensemble members or scenarios can be incorporated into the mean of the new model in some way. They might all have the same weight. And as such, for an ensemble member, sort of makes sense, because why would you put more importance in some ensemble member? And again, the same for RCPs. But also, everything what I just said now is still like computer theoretical. It has no sort of anchor to reality yet, because I mean, we need to sort of calibrate and validate against some real world data to see, well, okay, maybe they do need some weighting because some ensemble members, for whatever reason, they're not really that representative of past climate. So again, it might be the case that they didn't need different weight. I mean, the parameters will be sort of inferred. Some other stuff will be fixed. So yeah, again, that has to do with how when you actually do the inference and you calculate these things, you do your predictive checks, see how they match, how well they match, go back here, maybe incorporate an actual function here to transform them because this is insufficient, drop some of them, and so on and so forth. This is some real data. It's not going to be very different from the actual simulated ones, but again, real data from some random days for temperature. they look like this. I mean, okay, fine. This is actually simulations, just taking into account the spatial model, conditioning on some other ensemble member. Now, the point is, don't really compare the same day for the same day, because I mean, they're not going to be the same. The point is that it's just a simple model which you can sample inference from, and it's sort of trivial to calculate once you've done the inference. You can sort of recreate the main features of a map like this. This got simulated from running for however many days, weeks on supercomputer. This was sampled in milliseconds. And again, this is, keep in mind, this is from one value, one combination of values from all parameters. We have a distribution for all parameters. So 2 levels. We can take different combination of parameters from our posteriors, fix them, sample new data sets, which again, then there's an entire sort of distribution on every single point in the grid. Different combination of parameters, another sample, another range of samples, so on and so forth. The point being that through that you can capture sort of the uncertainty intrinsic into the simulation itself, the physical processes that the simulation captures, I mean the actual simulation, from the computer model, not the statistical one. The uncertainties in sort of having like a very rough resolution and other kinds of uncertainties. Keep in mind though that at this point you don't really differentiate them. I cannot like disaggregate these uncertainties and say each one is out of this thing, because I mean it's one unified model. You incorporated the uncertainties from every part and every level in the model initially, structured or not structured, as some other distribution, some other random variable. But at the end, sort of becomes one unified model, which you can again sort of get insights from. The second, the third one, again the same simulation by conditioning on more than one ensemble member. In this case, it's from actually another RCP. Again, they're not really going to look the same, or some days look very similar. But the main point is that it captures sort of the main variability you see in a map. And this is purely viewed as a statistical model. We have already fed it some, not real data, they're simulated, but some brains of real data, created a model which you can then sample from and take sort of, if you will, a representative distribution of samples, which can then, these kind of things can be fed into the next step, which is going to be the actual downscaling. But so far, we have almost everything to build across ensemble members and across RCPs a fully joined statistical model. Now, when I mean fully joined, just want to clarify, it's not fully joined across all parameters. All these things are going to run for each parameter individually. We're not going to run a fully joined model with all parameters, because it's all going to be impossible to run. I mean, these for so few parameters, for like the 6-kilometer data, might take 10 minutes, 15 minutes, 20 minutes, with just very few HMC runs. But the fully joined model for the 12-kilometer resolution data, I mean, it's never going to run. It's going to take as much time as the supercomputer took to run the actual simulations, which is useless. I mean, might as well run the actual simulation by then. So that's good. We have some sort of bedrock onto which we can build something and then do the downscaling properly. Although I didn't mention, this is just purely statistical, we haven't used anything else. What will be our fully integrated approach will be not just taking into account the other simulations, also incorporate into the downscaling step Ilya's and Jonathan's like mesoclean package and the mechanistic downscaling as the means for this thing. But that's again, it's not really the same level, because this is like pure the model across ensemble and RCPs. It's not yet the model for the downscale parameters, because obviously it's going to be 10,000 times more parameters and observations. It's a different kind of joint model. They are similar in functional form, sort of, but they're again separate. So that's fine. We sort of have a fairly simple statistical spatial temporal model for our observations that we can sample from. What's the next step? Well, the model again, it's very simple. It means we can run it a lot of times, we can tweak it around, and we can sort of run it a reasonable amount of time. But the point is that for wind speed, sort of fine. For the other parameters, not so much. The likelihood gets much more complicated. The field is not really isotropic or not really stationary or both. So we need to incorporate that into the likelihood, which means it can make the likelihood not a simple Gaussian as here or the actual model. It can make it into other things, which in turn means at some point we might not even be able to sample from it properly. It might become intractable, which needs other sampling methods, which thankfully I know about. But then again, you need to sample from, you need to write the thing yourself explicitly, which is fine. That's great. It's just going to take, the computational time is going to increase, not that much, but sufficiently. Now, what do I mean by sort of fancier random fields? Because everything I've said so far relies on modeling this thing as a Gaussian random field, which is very simple. We know both the moments exactly. It has only two moments by theory, and a lot of stuff that comes out of that sort of main mathematical description. Well, the point is, can we incorporate non-Gaussian fields? Yes, but you can convolve or add Gaussian random field and a sort of Poisson random field here to get sort of a mixture. Keep in mind you can combine different random fields such that the joint distribution is still Gaussian and the marginals are something else, or that the marginals are all Gaussian but the joint one is something different. That just sort of changes into what you're sampling and what you can actually calculate at the end, but let's leave that for now. Point is, for some climate variables, the field might have very strong directionality. The variance or the features, the size, how they are spread into the area can vary, and you cannot really capture it with just a Gaussian random field because it's going to be too rough or too smooth. Case in point is for a very nice paper that came out today. And this sort of perfectly captures like what you can do. Just two simple covariances. This is realization from some random field. You can capture almost a small eddy or an actual anticyclone that would be present in some time slices or multiple time slices of a climate simulation, which you would never be able to get something like that from just a pure Gaussian random field with just a structure effect. Even more exotic fields, the theory gets substantially harder, which is fine. We know how to deal with that. We don't know how to actually sample though from much more exotic fields. The point with those is that they can capture almost infinite variability, infinitely complex dynamics. But again, the question remains, is this thing going to run in the sampling step, which is the actual important step, in any reasonable amount of time, or the sampling of these things going to take even more than the actual supercomputer takes to output the climate simulation for 100 years? I don't know. We'll see. Yeah, that's it.
Thank you.
Thank you.